To start us off, we have Dr. Andy Wood.
Thanks. Great to be here again and see everyone. I want to try to tie this into some experience that we've already been having here. Yesterday in our work group meeting one with Katie Van Berkhoven and I, sort of talking to the group that's focused on advancing operational prediction. One of the main challenges that was brought up by people was the inability to know how to compare the work they're doing to existing work and find other baselines that they could use to say that their work was better or worse than what we already do. And so fortunately, this project kind of anticipated this challenge about a year and a half ago, when we decided that what would be critically useful for CIROH would be a test bed in which you can intercompare and establish benchmarks and provide like a rational, evidence-driven framework for introducing and selecting new science from CIROH. So that's what this project's about. My colleague Terry Hogue is a co-PI, and then we have a number of students that we're bringing in to work on it, and I'm still in a recruiting phase, as we'll see. So some of the key goals and objectives were first to kind of envision and establish this, not really a tool, but more of a program that encourages testbed thinking and benchmarking thinking across the projects in CIROH. So we would try to facilitate that with some guidance and structure, and then actually to dig back into some of the key products in forecasting, such as short-range forecasts or seasonal forecasts, and then try to estimate the benchmarks for those. It's really striking to me that in hydrologic prediction, unlike NWP or climate prediction, we have no idea what the status of our skill in forecasting is in the US or has been over the last 30 years. We just don't do verification, we don't track it. For something like geopotential height forecast score for Northern Hemisphere, we can go back 30 years and track how our skill has improved over those 30 years. We cannot do that in hydrology. So part of this project is to start to try to dig out all the data that we need to start to do that benchmarking. And so then we would also try to make this testbed a forum for interaction. And then some of the initial foci were probabilistic and ensemble prediction, looking at different model configurations and also probabilistic meteorological inputs. Some of the things that have been outlined as part of the, putting out a testbed implementation plan was the idea of first that forecasting focal areas for research can be not just the whole forecast or not just the model, but all the little pieces inside the data assimilation, the meteorological downscaling, the calibration method, and so on. And for each of these things, we can create an experimental protocol that has defined elements or required elements that help you with this benchmarking. And so some of those would be, first you define the objective, streamflow prediction, then you define and collect the observations you're going to use for verification and validation. Critically important, you define a reference capability that you're going to be benchmarking against. Hopefully that's an existing operational capability if it exists. In some cases it doesn't, so that you can say, I ended up 5% better than our current operational capability. And then the metrics of performance and the experimental design. What experiments are you going to run? Once the protocol is defined, and this would be done in a distributed way by people around CIROH working on those different aspects, it could be glacier modeling, and there are 3 groups working on glacier modeling. They would define the protocol, not me. Then it can be used to intercompare the research from the different groups in a way that we haven't been able to do before. So there have been a lot of interactions between the testbed, the CIROH hydrologic prediction testbed, and the evaluation tools team, certain other project teams, and then we should have more interactions with the cyber infrastructure because we'd like to leverage what they can offer. Some of the protocol design meetings, we're starting to kick off around streamflow simulation, snow estimation, short range prediction, and ensemble forces. Impact self-assessment, well, I started last February, so I'm not yet a year into my CIROH adventure. I think the major goals have been creating a kind of structured vision for how people can do the center comparison, and then starting to use this structure to design more rigorous evaluations, and just linking to other teams to try to socialize the concept. Next steps, start to develop the benchmarks, pulling in data sets, skill metrics for different parts of the capability, finalize the protocols around the number of different initial areas. We could end up with 24 protocols, depending on how the research in CIROH evolves. Maybe we'll only end up with 8, who knows? But I think if we can put this in place and people engage with it, then we have a basis for really seeing how all the research in an integrated way is moving us forward on different critical areas for forecasting. We haven't had that. I think we desperately need it, and so hopefully this will put together. That's where I am. Thanks.
As looking at the snow estimation protocols, I'd love to see that.
Yeah, so this, I have an implementation plan document that has been shared with a few of the groups where we have calls. We're putting together a website where we'll kind of outline this idea of a test bed for CIROH, and I've started to ask Ryan and some people in the snow group to put together a team for the initial design meeting on the snow estimation protocol. So, anyone who is working on that topic or interested could be part of designing that protocol. Key is, once it's laid down, we want to stick with it for a while. So we can, over a number of years, say, almost create like a leaderboard and for all the research that's coming out and say, okay, this appears to be the best that we have right now. And hopefully it's better than what we already do. But, we'll have to see. So Ryan would be the lead on designing or leading that team to design the protocol. Peter.
Yeah, so I have a suggestion for you and for all of you here, okay? For streamflow forecasting, to include in your reference, in your references, persistence in time and in space. If your model, any model, can beat persistence, then you can feel good about your model, I guarantee.
Yeah, certainly. I think a lot of the common, easy benchmarks like persistence are going to be a feature where appropriate, but even more important than that is pulling in benchmarks that reflect our operational capabilities right now. So for streamflow simulation or forecasting, we would take as one benchmark the RFC capability and the current NWM capability, because researchers here need to be able to compare their work to those baselines in a structured way. Okay, glad to get the assent of no more questions. Thanks.
Next up, we have Katie Van Werkhoven presenting on Integrated Evaluation System Prototype for Testing, Research, and Operational Advancements.
Hi, everybody. Thanks for that. Obviously, this project continues right on from Andy's project, and we've been collaborating really closely together. My team is myself, my co-PI, Matt Deno, who's out here in the audience, Sam Lamont, and John Park, who's also here. We've been working on this for the past year. As we set out, our proposed goals were to create a set of tools to evaluate hydrologic model and forecasts that are scalable and flexible. So obviously there's a lot of different work going on here across CIROH, and it's going to need to be evaluated in different ways, different variables, different data types. So we're trying to create a set of tools that can link to the test bed and be able to evaluate a wide range of different results. And that'll be open source, foster community development, so anybody can partake in the development of the system. And a second goal, very much coordinated with the test bed, is to streamline the use of evaluation standards so that results can be compared, as Andy was describing, across the different projects. So our key results from year one, we have a prototype system. We introduced this at the users conference in Utah in May. We're calling it TIER, Tools for Exploratory Evaluation and Hydrologic Research. So we needed a name for the repository. At the base level, it's a Python package at the moment, and it can be installed by anyone, used by anyone as a part of your research. You can do your own additional metrics with it, additional visualization with it. It allows for a very rapid, convenient way to join data and slice and dice it, so you can calculate metrics in different ways as appropriate or as defined by the standards. And then we're also on top of that building a number of Jupyter notebooks to demonstrate examples of using it, but also to provide sort of a starting point for different specific types of evaluation. Some of these we also introduced at the users conference in May. Some of them we've been continuing to build up since then. I'm building a set of Jupyter notebooks for post-event evaluation using TIER that I will share very soon. But it could be a wide range of different applications. And then at the top level, where logical, where it makes sense, we could turn some of those into servable dashboard web applications if it's something that will get a lot of use and it makes sense for users to have a much easier way to interact with it. So we didn't want to build just one tool that's constrained and requires a certain type of interaction. We wanted to keep it very flexible, both in terms of the evaluation approach and data types, but also in terms of the way that you all can interact with it. We also created the Python package and some of the repositories of Jupyter notebooks are on GitHub. Come see our poster for more of those locations, but there's the base tier repository there. And we've also created a Jupyter hub to help people interact with it and try out the examples and run their evaluations if they'd like to. Impact self-assessment, we met our year one expectation to design a prototype, to kind of the starting point, the guts of it, that meets the scalability and efficiency requirements. And there was a lot of research behind that Matt did in particular to figure out what is the back end sort of data structure that will enable very efficient evaluation and the exploratory type of evaluation that we really wanted to get at, where users can not only just get a bunch of metrics, but also dig into the data and understand where the metrics are coming from. We're currently using it, like I said, for post-event evaluation. We're working towards that, at least, and collaborating with other members of the CIROH community. And we designed an approach to do this dynamic evaluation that was lacking previously. Next steps, big next step. Our main focus kind of after this meeting will be coordinating with the test bed and designing, aligning with data structures, communication protocols with the test bed website, setting up, kind of codifying the protocols that Andy was describing so that people can design their protocols and then in a very streamlined way run the evaluation system for that protocol. We're also adding some functionality to that base package to do more metrics, more complex metrics that are based on thresholds, things that we know that are needed and are going to be needed for evaluation across the different projects. And we're streamlining the workflows to make it even more efficient than it is and enable those different types of analyses. So we'll have a poster, so come see us at the poster if you want to learn more details. Happy to take any questions.
Hi, Katie.
Hey,
This could also go to Andy as well. Andy and I were chatting last night, and like are you guys just doing stream flow evaluation, or are there gonna be the other like inputs and forcings that will be part of the evaluation framework? Because those can have, especially in a forecasting sense,
Yeah,
a
so
very
part of
big
the
impact.
post-event evaluation I'm doing is precipitation. It can be any variable, it's gridded point data. That's kind of the idea, is keeping it very flexible. So the tools themselves don't care what variable it is. It needs to be defined within the data structure what the variable is, but it could be any variable that's gridded or point at the moment. Mhm. Any other questions? All right, thank you.
Up next, we have Patrick Clemens presenting on the Northeast National Water Model Application Testbed.
Good morning. I'm Patrick Clemens. I'm the technical lead on this testbed project at University of Vermont. Seem Zia is the PI, and the entire Vermont FY22 CIROH team deserves co-authorship on this. As you can see on the poster, a lot of people's names are on there. This has been a truly collaborative effort, and I really appreciate everyone's contributions so far. So the main goal of this project was to establish some cyber infrastructure and a testbed framework to evaluate and provide R2O support for three test cases in Vermont. And we've already heard from two of these projects. The first is Beverly Wemple and Rebecca Deal's floodplain and channel routing representation. The second you'll hear from Andrew Stroth shortly, distributed network of sensors for improved nutrient load estimation. And then the third is you heard from Seem Zia yesterday on our HABS forecasting effort. And so the testbed is designed to support these three projects initially. So the key year one results, we've established some core cyber infrastructure to get folks kind of started with their projects. We have a virtual machine, some storage, and then a GitHub organization for code. We've created a number of tools for data access. So as folks want access to certain bits of data that are out there, whether it's the NWM retrospective or the forecasts or USGS gauge data or weather data, we work with our researchers to provide that code snippets for them to integrate into their workflows. And so we've created a number of those over this last year. We've also developed research frameworks. Guys are gonna get sick of seeing this picture to the right there, that workflow. It's our workflow framework for our impact models. And you saw it on a Seam slides yesterday. As we get the other test cases integrated, you'll see them using very similar frameworks. And so this is kind of our design. You see the feedback loop around the bottom as we hope to integrate some active learning into these workflows so that they continue to improve and get smarter as time goes on. And then we've also done a lot of robust outreach to other researchers and collaborators in the CIROH community. We hosted some testbed meetings early on with Andy and Katie, and we hope to continue those relationships going forward and kind of feeding off each other and sharing our work. So the thing I think has been most impactful over the last year is emerging as this integration and collaboration nexus for the Northeast CIROH folks. So catalyzing research, establishing best practices, providing common infrastructure, sharing things that are happening across CIROH with the local group. We meet twice a week. It's very well attended. To just kind of get a sense of what other things are going on across CIROH, especially in the realm of test beds, evaluation, and setting up frameworks. And so the next steps, kind of the idea is to continue to serve as that nexus and improve our tool set. So expand and refine our testbed services, again, continue to be a nexus and build more tools and algorithms for data simulation to work on that feedback loop and help make our impact models more to embed that active learning component into our forecasts. So that's it. Any questions? Oh, great, thanks.
Next up, we have Prabhakar Clement presenting on the development of benchmarking data sets for testing and improving next-gen national water model predictions with a focus on unsaturated soil and groundwater systems.
All right. Good morning, everybody. I'm Prabhakar Clement. I teach at University of Alabama. I thought I'll start with a little joke like Dan did. Let me see whether it'll work. Where can you find the ocean without water? On Zach's ball. Okay. So our project is slightly different. It's mostly looking at groundwater forecasting. Okay, so now when you think about groundwater, its soil is automatically connected to it. So what our project goal is, we got two project goals basically, primarily to build benchmark data sets. When I say test beds, it's physical test beds actually, building laboratory capabilities so we could actually do some experimental test beds for soil physics basically. The second one is kind of virtual test bed, which is primarily to map groundwater recharge, right? We also kind of leverage on another project I have, so it's kind of a combination of that work. This project actually funded a postdoc, and there was obviously some delays, and the postdoc came in January. So he's primarily focusing on the second objective. The first objective is based on some of the graduate students I had working on building a recharge data set. So what are some of the key results? So in terms of recharge data sets, we combed the literature. What we found was there is a nice data set put out by USGS based on taking a bunch of stream data and doing partitioning to find out quick flow, recharge, and they put a recharge data set. And that was validated based on 45 wells over the entire CONUS. That's all they had, they could find. So we said, okay, can we expand that validation database? So what if we took the Resetol recharge database and created our own data set and also look for other type of validation benchmarking ideas, okay? So with that, what we did was we took a very simple approach. We had a master's student, and so we worked with him, and he put a SWOT model for a river basin in Alabama, which is Black Warrior and Tongue-Bibi River Basin. We built a SWOT and said, hey, what would SWOT do? And then can we play games and compare REACH data with SWOT data to compare the recharge data set? And can we have other surrogates to verify recharge data? That's what we did. And we got kind of mixed results. If you look at the annual scale, it does a great job. Both products kind of match actually. Yeah. Both products match pretty well. That's a rainfall. That's a forcing basically. So both product match as well. And so we actually wrote a paper. We submitted a paper. The paper just got accepted. The problem is, as you go to a smaller scale, there is a lot of variation actually. So we're still playing on it. For example, instead of looking at directly measuring recharge, can we look at groundwater levels as a surrogate and to create some benchmark data set? So that's where that objective is there. The second objective is way more exciting, but I don't have too many pictures, but we got a very nice poster, and Dr. Nam is here. So please stop by our poster. So what we are doing is, we took, if those of you who looked at the soil physics side of the National Water Model, you got the NOAA-IMP's 2-meter soil column, right? Which is where all the soil transport processes are modeled. So we said, what if we created a physical test bed, which is basically literally a 2-meter soil column, and get some of the latest tensiometers, soil moisture probes, and instrument it so we could actually create a test bed where we can play games essentially and create a bunch of data set. And we did some background work, and what we are finding interesting is if you have a layered soil, truly layered soil, predicting information across the interface, it's not trivial. Okay, we could do a beautiful job if it's a uniform system and you rained on it or whatever. You can use Van Gunington, whatever this thing. But the minute you have an interface, there are problems. So we are working on a couple of interesting testbed data set where basically we would be able to have a 2-layered soil. And in the poster we talk about it, it's not yet done. We are still setting up all the instrumentation and everything. So that's where we are going. And then I got another master student working on various solvers. Can we simplify things? Do we have to use Van Gunington? Can we get away with simple things like Garner model, for example? Would that help? Can we, and also we kind of fumbled on an interesting formulation, which is, for those of you who looked at soil physics, you have a pressure-based formulation, water content-based formulation, and a mixed formulation. We kind of looked at a total head formulation, which is kind of interesting. I'm fully not sure what are the advantages we will get, but there is some potential in terms of improving the algorithm. So those are the things we are working on. Self-assessment, as I said, we have submitted a paper. We are fortunate to get it accepted. It's in press. This is based on the recharge data set. And then while working on this, the soil column area, we also obviously we need water retention curve and unsaturated hydraulic conductivity functions, which are not trivial to get. So traditionally we used to do pressure plates to do that, right? So we took this a primitive method called evaporation method, and that used to be a challenging approach. But now that we have a better sensors, better tensiometers, better soil moisture probes, we can refine that method. So that's what NAM has been working on. So we have a paper on how do we use modern data collection coupled to evaporation method. This is nothing to do with the evaporation, it's just a method basically to construct your soil water retention curves and unsaturated hydraulic conductivity function. And there is a draft paper you're working on. And there is another paper which is based on the benchmark data set we would work on. So those are the two things we're kind of working on. In terms of next steps, where do we go? So I got a PhD student she's excited about this idea of taking this recharge model data set we did and extending with the SWOT mod flow coupling. If you have a complicated model and a distributed model, do we gain anything? I don't know that. Okay, so use kind of, and we talked to the SWOT mod flow author at Colorado State. And we hopefully we will get something going on that to look at, can we refine this thing? And of course we have working on this the couple of articles on improving the soil water retention function and the unsaturated hydraulic conductivity functions, and then all these benchmark data sets, basically test beds on physical data sets essentially. Of course, I mean, I am always interested in the numerical side of it. So that's, even though it's not directly related to the proposal, we were playing with that. Hopefully we will get some ideas out of it, and we are not played with the next gen model, and we'll be happy to pull some of these routines out of next gen and play with some of the new codes Python tools we will be developing. So that's where we are at. Happy to take some questions. Thank you. All right. Thank you.
Okay, next up we have Giuseppe Torri presenting on an evaluation of the next gen national water model in tropical conditions with the aim of improving hyperlocal flood forecasting.
All right, thank you very much. Good morning, everybody. So I am the PI of one of the CIROH projects in Hawaii, and a bit like some of the projects that have presented before, we are also interested in developing a test bed for the National Water Model and for the Next Gen framework. And our main focus is obviously tropical conditions, and we are interested in flood forecasting, particularly for underserved and underserved communities in Hawaii. So for this particular project, as I said, we are targeting tropical islands, Hawaiian Islands in particular, for obvious reasons, because we live there. And we would like, along with evaluating the National Water Model, we would like to improve our ability to forecast flash flood events, which are pretty frequent during the wet season in Hawaii. And for this CIROH project, we have three main goals. The first goal is to develop some case studies that comprise different weather patterns that affect the Hawaiian Islands, and particularly weather patterns that lead to heavy rainfall events over all the different islands. We would like to create an observational based test bed that would help us evaluate the national water model and also the next gen national water model in the Hawaiian context. And also we would like to improve flood forecasting in Hawaii. And as I said before, we would like to target particularly underserved communities in Hawaii. In Hawaii, underserved from the point of view of obviously of forecast. In terms of key results for year one, we've been focused mostly on staffing. We've had some delays and some bureaucratic delays in that. So we've been focusing on trying to hire people to work with us, and we were able to hire 2 postdocs and a postmaster specialist to help in our project. The postmaster specialist helped us particularly working with the Hawaii Climate Data Portal, which is a data set that includes several variables that we're hoping to use for our evaluation, and that we're also hoping to work with the National Weather Service to integrate for their operations. One of the key outputs from the postmaster's work was the creation of relative humidity maps that will help us develop the evaluation test bed. One of the postdocs we hired worked in particular with USGS streamflow data and the National Water Model, and was able to create bias tables for the National Water Model. And the second postdoc was focused mostly on producing hindcasts of several flash flood events that affected the Hawaiian Islands. In terms of impact self-assessment, as I said, we had a bit of a rough start. We were able to get a no-cost extension, and we were able to make progress fast. And so we're hoping that year 2 would be we'll be able to deliver a bit more. I think that the work that the postdocs have been doing, quantifying biases for the National Water Model, would be very important in providing insights for the improvement of the next gen framework. And we've been working very closely with the National Weather Service to try and maximize our impact in the operational side. We're also hoping to work with communities to help the flood forecasting step. And finally, for year 2, the specialists will continue to work with the Hawaiian Climate Data Portal, and we're hoping to include sub-daily, hopefully hourly maps of additional variables. Key variable would be precipitation. We will also continue with building the evaluation test bed, and we'll start to work with the next gen framework. And we're also hoping to start with actual hindcasts and not just preliminary runs, but hindcasts of past flood events in Hawaii. Some of the results, if you want to see pictures, which I didn't include here, we have a poster today, and I'll be happy to show you the progress that we've made so far. Thank you. All right. I've received this question from multiple people. I have to say, living in Hawaii, we're always happy to get out of the islands once in a while. So we're happy to go someplace else. But yeah, we'd be happy to host the conference and see you all in Hawaii.
Book the travel arrangements. Okay, next up, we have Casey Calameo presenting on a collection of post-event flood inundation extent data via small unmanned aircraft systems for forecast evaluation services.
Right. Thank you, Zach. Good morning, everybody. I'm Casey Calamayo from the University of Alabama in Huntsville. Real quick, I just want to say that it means a lot to be here this week and connecting with our CIROH colleagues. This time last year, we were deployed for Hurricane Ian, so this is actually my first CIROH annual science meeting. So our project really focuses on 3 overarching objectives. The first one kind of being the umbrella objective of developing an effective means to use unmanned aircraft systems to collect to collect flood inundation extent data in support of model evaluation and forecast evaluation services. A major objective to accomplish that event or that goal is to develop the proper concept of operations, safety justifications, and apply for the appropriate waivers and research permits to fly UAS in some fairly complex environments. And finally, we really do want to engage with our stakeholders quite a bit in order to really identify whether or not our efforts are filling some of the data gaps and challenges in that sense. Year one results included finally getting access to our hardware and our UAS, our aircraft, as well as our payload, and really developing an efficient means to process that data quickly and deliver it to our stakeholders. I'll talk at the poster about some of the delays we had, unfortunately, including the drone manufacturer going out of business as soon as we got the funding and things like that. But regardless, over the summer, we were able to develop a operational capability to deploy in fairly short notice in areas of inclement weather and areas of flooding. Part of that includes developing that concept of operations or CONOPS and filling that with the proper waivers and authorizations to fly in those environments, as well as the special use permits to fly over federal land. The main reason we needed that research permit is because our study area is the Wheeler National Wildlife Refuge managed by the Fish and Wildlife Service in the Tennessee River Valley, which is home to a lot of different and unique hydrologic features, including the Deep River Channel in the Tennessee River, some of these Tupelo swamps as well, and some of the small streams and tributaries that are known to be underestimated in flooding from the National Water Model. And it's also home to several stream gauges and some proprietary gauges as well, managed by the local National Weather Service office. So our self-assessment with the overarching idea or expectation rather that we're able to kind of bridge this gap between model-based predictions and actionable information for end users. Our main goal this year was developing that operational capability, engaging with local and regional folks to identify those gaps and also help narrow down some of the selection criteria for flood areas or high impact areas. We were really fortunate to develop a strong means of communication with our local, so the Huntsville, Birmingham, and Atlanta National Weather Service offices and the hydrologists in charge there, as well as the regional river forecasting centers for the Southeast and Lower Mississippi. By way of the National Weather Service offices, we've also got a direct line of communication with both state EMA and the FEMA remote sensing cell. A particularly unique, I think, stakeholder that we were able to collect is the NOAA Unmanned Systems Research Transition Office, who picked up on some of the kind of complex operations we were trying to do in support of the National Water Center. And since then, we've signed on to a CRADA to be on a team for rapid deployment and damage assessment, as well as scientific data collection with NOAA on a different scale. So lastly, as far as next steps, we've got the operational capability. We have the regulatory compliance in check. So over the next year, we're going to be continuing to flesh this out, be able to process the data and deliver it effectively. We'd really like to engage more with our National Water Center customer and be able to identify what specific gaps we might be able to fill in that area. But in coordination with the local National Weather Service office, they've been extremely helpful and are really quite keen on engaging with us in that front. We did bring on a graduate research assistant to support in this effort. And one deliverable that we'll have coming out of this project in the next year is a template concept of operations, safety justification, and template waiver applications for other CIROH members who may be interested in implementing UAS, but flying in some areas that under, Basic 107 and Federal Aviation Administration rules and regulations is highly illegal without the proper permissions. So with that, I'd be happy to take any questions now, or please come by our poster as well. Thank you.
Hi, Casey. Beverly Wemple from University of Vermont. First, I heard last night that you're from Vermont. You were in Vermont in July, so I just wanted to thank you for joining the UAS response team. I have a question, but it's kind of a plug. I wonder if you've thought, I facilitated a table yesterday on educational initiatives that CIROH might advance. And I wonder if you've thought of working with Jarlath in Vermont on establishing a set of like mini institutes that you could take around to universities to train teams to do this rapid response. Our drone team in Vermont is like a bunch of super motivated undergraduate students that can have huge impact on like training up the next generation, serving communities when these events happen. What you're doing is just fantastic.
Yeah, absolutely. So thank you for your question. Yeah, first off, so I'm from Vermont originally, but I happen to have been in Vermont in July this summer. My mom was having surgery, but it just so happened the worst floods in recent history took place while I was there. So I was able to reach out, and we actually used some of the points from our CONOPS rather to be able to effectively use UAS in the disaster response effort. So thanks for that plug. As far as STEM education and community outreach, I think that would be a great idea. I actually just wrapped up a 3-year program sponsored by the FAA to get drones in schools to teach everything from photography to computer science, some physical aerospace education as well. And I would love to be able to implement that focused on hydrology applications and GIS and remote sensing applications. So certainly interested in working with Vermont on that front. And I'd like to also meet Lana Nations. I saw something on day one, I think, Dr. Burrian, about a drone camp. So I'd love to be involved in that if possible.
Yeah. This one. Yeah. Well, I have a bunch of questions, but the two urgent one that I have is, do you think you can expand it to urban flooding, actually fly over cities? And the second one, do you think with the tools, especially the processing tool, you can use, or you can apply them using imagery that someone else has collected? So old imagery, basically.
Sure. Yeah. So I'll address the first question first. So I'll confess we're in a unique position to be able to do some urban operations. My colleagues at UAH and I are working on helping the FAA define the rules and regulations and kind of open up the airspace over populated areas. So right now it is a little bit of a difficulty, I guess, in flying its operations over people. There's some really stringent rules, but yes, you can certainly, under proper safety justifications and taking the proper safety measures, you can certainly operate over that area. I think that would be a unique opportunity too, given the difficulty of collecting urban hydrology flooding. So yes, I'd like to pursue that. Your second question, I think so, actually. One of the things I'd really like to do with this project is take the concept of the proof of concept that we've developed in the Tennessee Valley and go to other locations, test this out in different geographic areas, work with different sensors, and determine whether or not, if you really need that $20,000 sensor or if a $300 multispectral camera can effectively deliver the same data. A key question on that, though, is the notion of scope, or rather scale. So for our purposes and for model evaluations, high resolution, very accurate data is probably going to be the most desirable. Whereas the emergency manager, they may not even necessarily need georeference data. They just need kind of a quick overview of what's happening right now and where they can properly assign resources and personnel. So yeah, I'd really be quite keen in identifying other sensors, use cases, and geographic locations to be able to do this, including drought, actually. So right now we're focused on flooding. It'd be really neat to see what we can do with low flow events.
Hi, Casey. And this is really a question to all the PIs that are collecting data. Is there a repository or just something as simple as like a Google sheet where people can put in, okay, this is the data that we're collecting, that we're generating. And for us other people, modelers, we can potentially look at what is useful and what can use, potentially increase the impact of the work. Of course, with some understanding of authorship.
Yeah, I'm not aware of anything across the Cooperative Institute for that, but I think that'd be a great idea, especially, as projects are, presumably purchasing some unique instruments or aircraft and things like that. It'd be a great opportunity for us here collectively to kind of pool some of those efforts and take some of the expertise from across the Institute. So yeah, I'd be happy to help champion something like that. All right, thank you all very much.
So I guess I was going to respond to the question about, is there a place to put data? I would say for modest sized data, you should use HydroShare. And as part of our project, we'll be setting up a group. So anybody in CIROH can be part of a group. And if you share the data with that group, anybody else will have access to it. So that would be a little bit more formal than a Google Sheets, but it would also allow it to be discoverable and have good metadata. So look out for information about that.
Oh, excellent. Thank you. All right, thank you all very much. I'd be happy to chat more at the poster.
Thank you, Casey. I'm from New York, and our local middle school just installed a drone flying course for students to learn how to fly the drones. So kids love drones. That's the moral of the story. Next up, we have Jason Cordera presenting on advancing the forecast skill of extreme rainfall events and the modeling of hydrologic response.
Thank you. Good morning. I'm here representing the team from the Center for Western Weather and Water Extremes at the Scripps Institution of Oceanography. Our FY22 project PI is Marty Ralph and the co-PI is Luca Delamonica. I am the atmospheric science lead for our center, and Ming Pan, also co-author here, is our hydrology lead for the center. Our FY22 projects focus on studying extreme rainfall events, their predictability, both atmospheric and hydrologic. We're focusing on atmospheric rivers, given our location on the West Coast and the importance of atmospheric rivers to West Coast water resources and water resources management. But we're also interested in exploring the role of atmospheric rivers beyond the West Coast in the central and eastern United States. So we sort of broke up our proposal and our work into two teams. The meteorology team is tackling the role of ARs in precipitation extremes elsewhere across the US, in addition to on the West Coast, studying individual events across the United States and their predictability. And then the hydrology team is working on the forcing side of things, developing a high resolution historical forcing data set at hourly and 1 kilometer resolutions to really dive into how well the high resolution forcings can be ingested by the water model and doing experiments to investigate AR prone watersheds. So we have a number of key one results. We took the method of let's do as much as possible all at the same time in parallel and just kind of move forward over time. We were blessed with a very active winter season that gave us lots of opportunities to explore high impact events in a short period of time. The image there is 9 different landfalling atmospheric rivers along the West Coast in a 3-week period in late December and early January last winter. So we focused on a number of different case studies. I highlighted the West Coast here, but also there were a number of atmospheric river events across the eastern US that we could focus on as well. We have a couple of postdocs here with us that are going to sort of staff our poster later and share some of the results. We looked at developing clustering algorithms to evaluate how ARs fit alongside other extreme rainfall producing systems like tropical cyclones and MCSs. We developed that 1 kilometer, 1 hour surface meteorological forcing data set. We did a long-term retrospective NWM simulation over many watersheds in the West. And that third bullet there, we also started diving into the role of ARs in precip extremes and the prediction of those events. So how'd we do? We think we did fairly well. We've furthered and developed and validated and enhanced a number of different things. I want to focus on the 4th bullet there. We enhanced and fostered new collaborations, especially locally with the California Department of Water Resources, also the California Nevada River Forecast Center, where someone from our center actually sits at the CNRFC. We have an embedded meteorologist and an embedded hydrologist. We're also developing and fostering collaboration with the Weather Prediction Center to talk about QPF and QPF skill. And then we are supporting 4 postdocs and 2 early career scientists on this FY22 project, either as full FTEs or partial FTEs. Next steps, like I said, we took the paintball approach of trying to advance a number of different projects all at once. So we're going to continue making headway on AR science, precipitation forecast skill, and hydrologic modeling. And like I said, there are 4 of us here that will be at the poster that could discuss more of our research if you have any further questions.
Me? Okay. Can you, really interesting, thanks. Can you tell a few more details about your forcing data set? What variables does it include? Does it include all the variables that you need to simulate process-based models? And can you talk about the domain, if it includes some of the transboundary watersheds?
That's a fantastic question for my colleague Ming Pan. I don't see, is Ming still here? Taylor, can you speak to that data set? We'll follow up directly with you afterwards.
Thank you, Jason. Next up, we have Goye New presenting on advanced land surface modeling coupled with next-gen national water model and integrated with NOAA UFS to improve hydrologic forecasting capability.
Good morning, everyone. So my name is Guoyuan Yu. Actually, I'm not Thai. Okay. Yeah, here I'm trying to report this. This is a given title by Steve. I think advanced land surface modeling coupled with a next gen national water model and integrate with NOAA UFS to improve hydrological forecasting capability. Okay, we're working on two different model systems. Okay, this is the proposed goals and objectives. So first goal is to integrate an explicit preferential model and plant hydraulics into NOAA MP, which used in the UFS system for weather forecasting and also for the national water model as OWP module. And second goal is to implement some new soil hydraulic data sets, including machine learning based data sets, hydraulic properties into the land surface model, NOMP, and then couple the updated NOMP with UFS and also next gen. So for the first year, we published a paper on like frozen soil effects on stream flow predictions, published on WR already. And most people think that the presence of soil ice block the water flow. Actually, our work demonstrates that these effects should be weaker in the model to improve stream flow predictions. Otherwise, it's too strong, the prediction scale will be lower. And second work, we've developed an explicit preferential flow model based on the mixed firm recharge equation, which solves pressure at the same time conserve mass. Okay. And this work already submitted to WR, and there's some results. So the new model can explicitly represent surface ponding. Here I show the importance of surface ponding, especially in the central United States, kind of lower Mississippi and surrounding areas. And also the shaded area shows how important surface ponding. Okay, for stream flow predictions, we have upper bound, lower bound. Like we have to determine that a threshold, okay, ponding threshold to link local pondings and to determine hydraulic connectivity. Okay. Also, this model can represent preferential flow. When we include preferential flow, it mainly improves all the subbasins, HAC2 subbasins within the Mississippi River Basin. Mainly for low flow cases, it doesn't affect very high flow peaks, but low flow or recession period or some peaks, low peaks, okay, low peak flows. The third work, we will already set up the next gen model for 2 catchments in California. We already set up the process using the hydro fabric to develop like catchments, flow lines, and downscaled NL-2 precipitation. After downscale, so the quality of precipitation and also temperature improved up in the mountains. Okay, next steps. Now we have 2 postdocs working on each of this model system. First, we are coupling NOVMP with the next gen, trying to update the OWT module to include preferential flow and also plant hydraulics. And the second postdoc are working on like NOVMP to update the land surface model within NSAP UFS. trying to improve like weather forecast or seasonal forecast, climate predictions. Okay, that's.
Good morning. Very interesting talk. Appreciate your work. I'm curious, you say you set up the next gen model. There is no next gen model, there's a next gen framework, and it allows us to run formulations and catchments.
Yeah.
Which formulations did you run?
Yeah, we set up the model like CFE coupled with NOVA module, like the OWT module together.
Oh, okay.
Yeah.
Okay, thank you. That clarifies.
Yeah, we're trying to test this and improved version over these two catchments, like California. We also set up in Arizona, yeah, the catchment of this model. We still have a little bit of problem. I think my postdoc already talked to the National Water, James, maybe, yeah.
Okay, thank you.
Thank you very much. Next up, we have Hamid Mordekani presenting on data assimilation and fusion for operational next-gen national water model and enhanced hydrologic forecasting framework.
Good morning, everyone. Well, I'm Hamid Mordekani, as Zach introduced. I'm the PI of this project, and I'm assisted by several great scientists, including KJ and Kayhan sitting back there, and a couple other PhD students involved in different aspects of this project. Well, as you know, the operational forecasting system currently used in the United States basically integrate data assimilation with numerical weather models to improve the meteorological forecast. With the growing access of environmental earth science and earth information available to all of us, we were highly motivated to use this data and integrate the data assimilation frameworks, a formal data assimilation framework, into the conceptual functional equivalent model, CFE model, which is a simplified version of the national weather model, to enhance the forecasting skill of the operational forecast system. Basically, our research goal is to develop a hydrologic forecasting system to integrate data hydrologic models with data assimilation techniques within the next-gen national weather framework. And with that, we are using a mixture of remotely sensed satellite data products and in-situ observation to actually assimilate using different filtering techniques we've been developing over the years into the CFE model. We got some preliminary good results. I'm not including those, but I'm going to focus on some other things, especially the research objectives here. As you know, the most erroneous component of any hydrologic modeling is the forcing data, basically the precipitation data. And the current practice in data assimilation is to simply perturb the forcing data from any forcing data of interest. We perturb it, we just drive the hydrologic model with that, we do the data assimilation, and we say, okay, we characterize the uncertainty in the forcing data. But this is a rather naive approach. So we thought, okay, let's develop a data fusion approach, and we combine the skill of different remotely sensed products and come up with one single product that is more skillful and more accurate than any of these individual products. I'm going to show some results after that. And then it's going to develop the data assimilation system that's going to be the next phase, and also the extending the framework to drought monitoring over the continental United States. So here on the left, you see 7 different satellite products from CMORPH, Persian, IMERG, etc. And we developed a deep learning approach based on convolutional LSTM and convolutional neural network approach to fully exploit the spatiotemporal patterns of this data set. So we basically merge and downscale these products, bringing them all to the same scale at 0.1 degree of spatial resolution. On top left, you see the PDFN, which stands for a Precipitation Data Fusion Network through this deep learning approach. And I'm showing the KGE performance measured and showing that this PDF-N has been doing much better than any of these individual products. So we are having a poster. We are gonna explain the result in more detail. If you're interested, please stop by. The result of this paper, study was published in Remote Sensing of Environment, and Kayhan, who's sitting back there, has been a great help in developing this approach altogether. On the right, you see the post-processing of CFE, because as you know, if you want to do any data assimilation, any hydrologic modeling, first you start with model calibration, but there is no such a thing as a perfect model parameters. Even if you do the perfect model calibration using global optimization techniques, because of the non-uniqueness and equifinality that Xiaopeng also mentioned yesterday. So we said, okay, after we do the formal model calibration using the best available global optimization technique for the CFE model, let's do post-processing and further modify the model forecast from the CFE. So we use a bunch of different techniques, LSTM and simple neural network, convolutional, etc. And finally, we combine them through the Coppola-based Bayesian model averaging technique to account for uncertainty of all these techniques. And as you see on the green bar, the performance of the Coppola-based Bayesian model averaging is better than any of these individual neural network-based products and techniques. So I'm having that paper at hand. I'm editing that, and we are going to submit that as a second paper of this project. So the impact assessment is that, well, we improved the data fusion approach for precipitation products. So we have the data ready. We are trying to make it available publicly on our website. And we are trying to automate that everyone can use those products. And the next step, I would say, is to develop the data assimilation. And we have developed the data assimilation, and we have done some preliminary work on a synthetic base. I explained to Fred yesterday, but I didn't include that result because I want to make sure about everything that is working perfectly before reporting that. And then next year, hopefully, I'm going to show some real data assimilation in addition to synthetic ones as well. And after that, we are going to do this for streamflow forecasting and eventually for drought monitoring, as we promised in the proposal. Thank you so much. If any question, I'll be more than happy to answer. Thank you.
Thanks very much. Next up, we have Andrew Scroth presenting on leveraging. We're 35 minutes ahead of schedule, so I don't know if you want to just keep going. Break was supposed to be at 10 a.m. Was there supposed to be break food, Steve? No. That's mainly why I kept going. So keep going till the food shows up, and then we'll take break.
Great, nice to see everyone again. Here we're going to be talking a little more about a project we're working on in Vermont that, of course, is important given everything that we've been hearing about the floods that we had this summer, which is trying to improve the capacity of the National Water Model to provide useful flow information in montane forested headwaters, which are kind of the dominant watershed in much of our communities in Vermont and elsewhere in the Northern Appalachians. They're kind of underrepresented in the gauge network, so the National Water Model isn't seeing data that's coming from those particular systems, but they generally force a lot of the damage that we see downstream. I'd like to acknowledge my collaborators, particularly our postdoc, Mircea Morales, who's done a lot of this work, but also my collaborators, Beverly Wemple and Kristen Underwood, John Kemper, and Satish Surchan, Jamie Shanley at the USGS. So again, our goals are kind of multi-pronged, but are aimed at getting a better forecast in these particular systems. Our first approach was to assess the performance of the National Water Model in these forested montane headwaters where we have USGS gauge infrastructure with the retrospective. And I guess our thoughts were there that we could look at how the retrospective was performing. We'd have the best meteorological forcing data with a real analysis product, so we could limit the, which, yeah, Brett's laughing, that's probably not accurate, but to look at least isolate more of how the model's doing in those systems, and then kind of limit the problems that we might have with when we're using the actual model forecast products. Another component of this is to deploy in situ water level monitoring networks above and below the gauge infrastructure. And we did this in concert with a lot of the stakeholders, folks that actually didn't even know the national water model existed, but folks that are responsible for kind of managing town infrastructure and road infrastructure in the state, with the idea that they could do this themselves with particular infrastructure that they were concerned with, and try and predict water level and damage with a given national water model flow forecast. And ultimately, that's where we're kind of going in years 2 and 3. So what our results look like? Key results, of course, new hires. We've hired high quality postdocs. We've assessed our national water model performance at our focal sites where we have gauge data. And here you can see a hydrograph from those sites. This is averaged for the retrospective data, and you can see the offset is not subtle, and presumably that makes it correctable. And in particular, what we're missing is the snowmelt derived component of the hydrograph, right? So that spring big pulse where most of our water comes out in these systems. Impact self-assessment, we had a little bit of delay again, and this is similar to what happened in one of my other projects where it's just hard to recruit postdocs in a timely manner in year 1, especially when they're coming from outside the country. But we hired a high quality postdoc and a technician, in this case by happenstance from traditionally underrepresented STEM backgrounds. Stakeholder engagement, again, at the front end of this project with folks that, again, don't really know what the water model is capable of. So I think we can bring this to those kind of folks that are operating more in the town kind of infrastructure scale. We've submitted a number of conference abstracts that are based on those first 2 objectives. Like I mentioned earlier, that error, at least in the retrospective, appears systematic. And thus correctable. So we can now start to work with more complicated models to predict loading or nutrients again, flow in some of these basins, with the idea that, in Vermont we have an opportunity to leverage a number of different gauge sites that my group and other groups in the state have been maintaining that the national water model isn't seeing. And so I think where that's cool in future years is that we can start to look at, if we develop a correction model for forested montane headwater systems in one particular catchment, can we start to project those forecasts and improve those forecasts in ungauged basins that are elsewhere within the system? And so we have this kind of 2-pronged approach moving forward to make progress, one of which is predicting water level at key components of infrastructure and different channel environments across downstream of our gauges. And then 2, can we try to do this in ungauged basins by leveraging some of the sites that the water model isn't seeing right now. That's all I've got. Happy to take questions. Also would love to see folks in my poster.
Hi, Andrew. I was left. So we found the national water model to do actually, retrospective, do fairly well in semi-headwater catchments, basically where there's a USGS gauge. Could you explain a little bit what you mean by, what are your headwater catchments? Like, what's the size of the catchment that you're looking at?
You're looking at small catchments, so it depends on the sites. We've got 3 gauge sites, but the one that I'm working at is like 40 square kilometers.
Thank you.
But much lower relief than what you're seeing in Utah, obviously.
Yeah, I appreciate the presentation.
Thank you.
The USGS, I think you pointed out, traditionally puts their gauges on high stream orders, big basins all the way down. Is there any vision to effectively install gauges on lower stream orders that maybe are lower cost that the USGS would operate in long term? Maybe it's the DOT. I'm not sure kind of where you're going with that, but I think if you do that, you might start getting a better understanding as to what's happening at those kind of ungauged levels at scale. And I think that's kind of where you're going. I'm just curious what your angle of attack is to try to solve that.
Yeah, I think our angle of attack, at least how I mean, because there's a fair amount of work that goes into establishing a rating curve, right? And that might not be feasible for these kind of entities at scale, but I think establishing a pressure transducer that's measuring water level would be feasible across scale. And that's, you know, it's $100 of sensor infrastructure, relatively simple technology. That would be how I would go about them. I'm not aware of USGS plans to follow up on this. I know their gauge installment is very expensive. Thank you. Please come.
Thanks very much, Andrew. Okay, not to do this to you, John, but between us and the break, we have John Beck pinch hitting for Sarah Graves, presenting on adapt precipitation, super resolution and data fusion, deep learning techniques for operational flood forecasting. Before John begins, I'll just ask if we could keep the chatter down in the back. We're ready for the break right after this. Thank you.
Okay, good morning. My name is John Beck. I'm at the University of Alabama in Huntsville, and we've been doing research on what we call super resolution, which is improving the resolution of data, in this case, space-based precipitation data. So the overall goal of our project is to improve operational flood forecasting by using deep learning to enhance the resolution of space-based satellite precipitation data. Take those results from our super resolution model and estimate rain rates. With those rain rate estimations and with our better resolution product, we would like to develop a rain rate product that could then go into NOAA's national water model. So kind of in general, the summary of this is we're looking at taking the NASA Global Precipitation Measurement Mission, the GPM data, which is about 4 kilometers, and we're using the MRMS 1 kilometer data, the ground radar data, as ground truth, and building convolutional neural networks. We're getting the training data from NASA's, NASA has a GPM validation network, and in that validation network, they have coincident pairs of both the GPM data and the MRMS data. So it's a perfect bed of data that we can use for our training. So our specific objectives include developing advanced CNNs to help with this process. We also are looking at new pre-processing techniques, changing some of our experimental parameters, and actually developing our own specialized loss functions in our network. When we develop our product, we're hoping to test it in areas where ground radar or the MRMS data is lacking, and that would be the real power of this product. And we'd like to ensure that these data sets meet the file and metadata standards for the National Water Model. And then we'd like to test that within the National Water Model in year 3. So our key results from year 1, we were able to successfully develop a training set out of the GPM validation network, and we completed basically a prototype of a basic CNN that would increase the spatial resolution of the GPM data. We used approximately about 16,000 image pairs from this GPM validation network to train our CNN. We also realized that we needed to develop a module that would test a specific module of metrics that would test our results, because basic spatial statistical tests such as signal to peak ratios were just not adequate for this type of data. And we also developed a cloud-based, using Amazon Web Services, user interface that lets us access the data, visualize the data, and then process the data using Amazon SageMaker for our deep learning network. So our results, we're really happy with our prototype that we developed in year 1. We also identified a use case where a hurricane had knocked out a radar, and so we're looking to get the GPM data for that area to test our product. We also had 3 graduate students during the first year that worked on some of the deep learning model, and with that they gained valuable insights on machine learning and with using precipitation data. It's hard to kind of evaluate the broader impacts just after 1 year, but we think that this product could be groundbreaking in order to provide more rain products in areas where MRMS data is lacking. And we will present the findings at AGU this year. Our next steps, we're going to back up a little bit and look at some more pre-processing steps in our training data. We found throughout year 1 that we could probably improve our training data set. And we're going to introduce a GAN into our CNN architecture to try to match up our time sequences a little bit better. And I have a poster if anyone wants to talk about that step. I've got it illustrated a little bit better in our poster. And then we would like to get some of the GPM data that's outside of the validation network and run it through the model. And we've also have an idea of estimating rain rates for offshore hurricane events using our model. So with that, I'll take any questions. Guess everyone's ready for a break. One question.
Yeah, this is super interesting. Can you elaborate on, I guess, the extent to which you can increase the resolution?
So
if there's a theoretical maximum?
Yeah, so we're taking the 4 kilometer satellite data and increasing it to the 1 kilometer, which is our ground truth, the MRMS data.
And do you know, is there like a potential limit given something like, say, atmospheric turbulence? Do you have any idea if there might be like a future limit to how much you might be able to apply this technique?
I think with having all the training sets at the 1 kilometer, I don't think we would go any better than the 1 kilometer. Yes.
You mentioned 4 kilometers. Are you using the radar data or
The,
what GPM data are you using?
It's radar data from the Global Precipitation Measurement Mission. It's a NASA satellite constellation.
Yeah, I'm familiar. So you're using DPR.
Yeah, DPR.
estimates.
Yeah,
Okay.
yeah.
Thank you for the fantastic presentation. So you mentioned GAN in your one of your objectives, and I was wondering, since GAN is usually used for generating new data, are you going to use it for creating synthetic new data or just a prediction of 1 kilometer precipitation? Thank you.
Yeah, I've got some examples in our poster, but what we're hoping to do is we're going to try to build a GAN within the MRMS data to predict in between time sequences so that we can match up our GPM data better.
Thank you very much, John. You may usher us into a break.
How many minutes?
We'll reconvene at 10 o'clock, Steve, 10:10. 10:15.
We will reconvene in 10:15. Thank you.
The break came at an appropriate time because now we're going to transition into frozen water. The next several talks are snow related. And to kick us off, we have Mackenzie Skiles presenting on improved representation of snow accumulation and melting processes in the next-gen national water model in support of the seasonal to subseasonal water supply forecasts.
Hi, everyone. Sorry, that title is kind of a mouthful. But just as slightly further introduction, I am the director of the Snow Hydrology Research to Operations Laboratory at the University of Utah. And our CIROH projects are focused on snow hydrology. So I'll be presenting results from our FY22 project here. So the goals of our project were to run National Water Model NextGen in snow-dominated headwaters of the Colorado River Basin within the Colorado Basin River Forecast Center forecast region. And we wanted to benchmark the performance of the current national water model against snow observation sites, LiDAR mapped snow depth to assess as a baseline how well snow is represented currently. And then use different methods to improve representation of snow cover, including producing machine learning based snow depth estimates over the snowmelt dominated Colorado River Basin, and then to test integration of different data sets, both on the forcing side and on the snow state variable side. So that includes improving precipitation using precipitation from numerical weather prediction, remote sensing variables as updates to the forcing variables, and then to improve the snow mass balance, integrating or assimilating things like machine learning based snow models. Okay, so generally what we found is that within the current national water model, snow is underrepresented. There's a low bias, which obviously leads to errors in snowmelt timing. If we can integrate updated precipitation, we can improve the snow mass balance. We can essentially match peak SWE, which is the target that we're going for. And then if we incorporate remotely sensed snow albedo to update the net solar radiation, then we can improve snowmelt timing and reaching both matching peak SWE and then snow depletion date and snowmelt rates as what we are going for. And then on the machine learning side, these are sort of two separate tracks at this point. We have not assimilated the machine learning SWE into the model yet, but there has been progress made on the machine learning side. It is running over the full upper Colorado River Basin and other parts of the Western US as well. So in terms of our impact self-assessment, we met our year one objectives. We had similar sort of hurdles that other projects had, and that we started a little bit later than we wanted to, and it took a little bit longer to hire the postdoc on the project. But still, we've been able to make relatively good progress in year one, doing the initial model assessment on the retrospective national water model runs, and to determine areas of improvement, and being able to identify which data sets could lead to the improvements that we are looking for in terms of snow representation. And we've been able to demonstrate those improvements. Right now, we're working in just an instance of the model in a few watersheds. We just recently got out watersheds over the whole upper Colorado River Basin, but we have not actually assessed all of those yet. But using a single catchment, we are really excited about our early results. And then in terms of the machine learning model, we've been able to produce near real-time estimates of SWE across large regions of the continental US. And I'll just point out that if you have any questions about the machine learning, we work closely with Ryan Johnson, who's giving a talk, not next, but after that. So you could hold questions about the machine learning stuff for Ryan, passing the buck there. Okay, so the next steps is to continue refinement of the snow modeling, an expanded number of assessment catchments and assessment data types. So, you know, we obviously could be exploring different precipitation data sets. We could be exploring different types of remote sensing products for assimilation. One of the ones that we're targeting is GOES cloud cover to update cloud fraction. And then continue development and refinement of the machine learning suite. And I will stop there. Any questions? Oh, yes.
So, earlier you said you set up NextGen in the Colorado River Basin or in catchments?
In catchments, yeah, we're doing it at the Huck 14 level, so yeah.
Which model formulations are you using?
We were looking at the National Water Model retrospective runs currently, but now that we have it set up in the NextGen framework, we can pull in we can pull in other representations.
I would be really, you know, we have developed a BMI module for NOAA MP that includes
Right.
its snow representations. We would be very interested if, I know you've got access to other snow model codes. If you could work with somebody to convert those to a BMI interface and include those and test them, that would be awesome.
Yeah, so the instance that I was talking about, and it's the East River watershed in Colorado, that's NOAA MP, as it is in the National Water Model. And then we are in FY23, we're testing another snow energy balance model in the next gen framework.
Okay.
Yeah,
Great.
but we're open to if people have other models, other snow representation models that they would like to compare, we're happy to do that as well.
Thank you.
Thank you.
Next up, we have Anna Barros from University of Illinois presenting on satellite remote sensing of snow water resources and hydrologic prediction.
Okay, thank you very much. So our project is, I'm going to move into the first page of the slides. It's really about using synthetic aperture radar, retrieved snow water equivalent, snow depth, snow density, and assimilating that into models, hydrologic models, and improving water prediction in general at seasonal scales, at diurnal scales, and so on. And now, the important contribution, I think, of why we need to really pay a lot of attention in terms of what we're doing here is that we want to assimilate remote sensing measurements themselves. So in this case, using synthetic aperture radar, it would be radar backscatter, and also the retrieved variable. So what that requires is that we have a snow hydrology model that's a multi-layer model, and we also have a radiative transfer model that's also a multi-layer model. And so we'll be exploring both pathways for data assimilation. And this comes from early, actually 2000s, late 1990s, when the ECMWF was doing way better in terms of precipitation data assimilation, or the impacts of precipitation data assimilation in the operational models as compared to what the National Weather Service was doing, right? And the reason was because the National Weather Service was using retrieved precipitation and then assimilating precipitation into the operational model, whereas the ECMWF took the route of using radiative transfers and basically assimilating the observed brightness temperatures and so on into the model and then convert that into the physics. And so we're going to explore both of them because we know that the measurements, wherever we take them, they are what they are, right? Whereas in the models, we may have biases locally and so on. And so this gives us an opportunity to look at them in different ways. And that's what we're doing. Now, Prabhakar is working on this problem, and as with everybody else in this room, it took us 9 months to be able to actually get him legally hired and officially employed. And so he only really started working on the project in late May, beginning of June, right, Prabhakar? I forget. And so I had a graduate student working on this before, but and so we're doing, all of these sort of preliminary tests using actually data from NASA SNOWX experiments in Colorado, in Grand Mesa, and these results you see here are for just point assimilation. We're not very confident, for example, of how good our forcing is in this case because we're using data from local stations, but what you can see is that by doing the data assimilation and actually using this information, redistributing it through the snow column in terms of the multiple layers of snow that have different density and different microphysics, we can get really good results in terms of the data assimilation. And the importance of this is, for example, that for a difference of about of about the value of this data assimilation, right? It's an improvement in the prediction of SWE of about 40% at the end, at the beginning of the full melt season. And really, in terms of timing, it's 1 month of difference. We don't expect to be able to do it this well everywhere, of course. And Prabhakar now is going to be exploring also error models for our observations, because we don't have that under as much control, or in terms of what we know is happening in nature. The other result that I wanted to show, and this is really the promise of synthetic aperture radar. So we had some flights during SNOW-X with an airborne synthetic aperture radar that measures X and KU backscatter. And we developed a retrieval model using exactly the same framework, the same snow physics, and the same radiative transfer. And you can see here our retrievals, the spatial maps of the flights, but also the snow depth comparisons with LiDAR observations at the same time. And so, this is really exciting. We were very happy with these results, because what they show is that if we can do this well, right, with airborne synthetic aperture radar, if we have a satellite, we'll be able to do even much better, because in these cases with airborne, the observing geometry is changing all the time, right? And we have all kinds of artifacts. It's very unstable measurement. Every pixel is a different pixel, whereas with satellites, it's a fixed observing geometry. And so we'll have much better control of the observation model. And in terms of what we're going to do next, in terms of the impact on self-assessment, so we have the overall framework developed. We're using DART and adapting DART to this problem. Of course, the big innovation here is this redistribution of the information in the vertical, and looking forward to next year and all of these kind of things. Okay, to do. It's a long list of things to do. We have a paper in review on the retrieval demonstration. Thank you.
Yeah, hi Anna. That was a really nice presentation. Thanks. I'm over here.
Oh. And I have my glasses on. Imagine if I didn't.
Right, I know that would be suboptimal. No pun intended. The open loop simulation, you said that you perturbed precipitation. And can you talk a little bit about how you represented, the model error? Are the perturbations in precipitation constant in space and time? Did you perturb other variables? Did you perturb the model?
All very good questions. We're working on all of those issues, right? And we actually, so in this case, we're using only precipitation is actually being perturbed with 40%, and so because we don't actually know what the uncertainty is, we didn't use her. I have other work that's not in the context of this project where we use her, and her gives us actually very good simulations. And so the open loop simulation would have been better than this one in this particular case. Yeah. But we're using the observations that are available at this particular location where we have all the other observations, so we can compare them. Okay. Yes. But yeah, and Prabhakar used also inflation of these different ensembles and so on. And now we really want to focus though is on the error of the observations, on the model error on the observational model error model. Yes. Thank you.
Thank you, Anna. Next up, we have Ryan Johnson presenting on machine learning to advance national scale snow water equivalent modeling.
All right, so Michael gave me a good talk before this. He told me not to put you guys to sleep, so I will absolutely do my best to keep some energy up here. I know everyone is excited to get kind of out and finish with all this stuff. Yeah, so we're using machine learning to advance the kind of the state of the snowpack for the national water model, and working closely with Carlos Arroz at University of Utah, and then of course Mackenzie Skiles, kind of like a collaboratory project right here. All right, so proposed goals was to make a model. We worked for a project with the U.S. Bureau of Rec to use machine learning and to develop a prototype of a model that can make near real-time snow water equivalent estimates. We wanted to benchmark the performance of the model on NASA ASO data on their observations. So that's key areas in the Sierra Nevada and then in Colorado. We wanted to demonstrate near real-time predictive capability. And then a key thing is we wanted to create educational materials. Machine learning is a hot topic right now, and there's not a lot of actual use cases that are out there. There are all these curated data sets. And so we wanted to show students how to go get the data, process the data, train a model, feature engineering, feature selection, how to evaluate a model. So those were kind of our goals going into this project. All right, so key results. So we built what we call it a fitting name, the National Snow Model. That was not taken yet, and when there's the National Water Model, that's what we named it. It makes near real time 1 square kilometer. I'm sure Ed is going to cringe when I say it's a gridded data set, but that is what we were kind of given as this framework for the U.S. Bureau of Reclamation. And we had a great discussion yesterday how, what the future version will be to not use a grid. But it makes 20,000 square kilometers. And it actually just grew, as Mackenzie was showing. It can be continuous, spatially continuous for the entire upper Colorado River Basin. It has a low RMSE at the current point. And then we do, that's just a lot of test and bias. And there's just so many points that are low snow that it makes it look like, it makes it look better than it really is. We developed a start to finish machine learning tutorial for education and outreach activities. We work with our partners over at the Earth Science Information Partners to develop some educational materials. And then we were talking to people from HydroLearn here at the conference, and hopefully, kind of get these machine learning tutorials implemented in some learning materials. And then we also have a drafted manuscript ready, almost nearly ready to submit to environmental modeling and software. So a self-assessment, version 1 is a success. It works. It ran every day on my laptop in under about 10 minutes. So let's go to getting a bunch of SNOTEL data. It's processing the data, making the prediction, and then going either saving the data and making visualizations as we see right here. That is a prediction for back in March. And we had a very big snow year, so it was exciting to see the results happen right there. And there is areas where there should be snow predictions, but that's just the current extent of our modeling domain in the Sierra Nevada mountains. Benefited some workforce development. This project supported an REU last year. We were actually making snow predictions where there was no snow. And so how did we fix that? We brought in, an REU student, and he used NASA VERS data, fraction snow cover area, to essentially constrain the domain. And what that did is now we're making predictions where there should be a snow based on remote sensing satellite imagery. And then we developed multiple presentations. The key one was HU last fall. Next step. So we're going to more constrain the modeling domain, other remote sensing products. Just as we were chatting with Ed yesterday, we're going to try to include representative energy and mass balance components to the framework. We want to improve transferability. So can we train a model on the the San Juan Mountains in Colorado and have that make predictions elsewhere in Colorado? How's performance right there? Also, in chatting yesterday with the NOAA team, we needed some kind of standardized evaluation framework. There's no standard evaluation, either data set for operational snow prediction. So we already started development on Suite, which is a standardized snow water equivalent evaluation tool. And so that's something, if you do snow, please contact me. We were working with Andy and kind of creating a framework so we can test these, any kind of snow model. And then we're going to be working on creating spatially continuous predictions for the Sierra Nevada mountains. And we're done. Questions? Adrian.
Thanks, Ryan. I had 2 questions. One is I was curious to hear about what kind of machine learning algorithm you were using. And then also I saved a question from Mackenzie's talk for you, since she said to skip to you. It looked like there were some kind of geometric artifacts in the SWE maps that we saw from Mackenzie. And I was curious if you looked at those and where you thought they might be coming from.
Yeah, 100%. So, it's a 3-minute talk, so I was very short. We looked at XGBoost, light gradient machine learning algorithm, and a neural network. We will be looking at LSTMs in the future, but we currently it's a neural network, a deep neural network. Last year, if any of you guys ski, we had a greater than a 2-month snow drought. And the neural network was the only model that actually showed snowpack decreasing due to sublimation, where the tree-based models kept snow increasing. So hopefully that answered question number 1. And then to your other question, we have 23 different regional models. We wanted to connect the in-situ observations and with the respective modeling domain. So a snow-tail site in the Southern Sierra is not going to inform a prediction in Northwest Montana. And so what you probably saw in those images is those are very preliminary. Those were done very recently. And those are the differences between the two modeling domains. Yeah.
I have a quick question, Ryan. Very interesting. Are you planning to coordinate with anyone from like National Operational Hydrologic or Remote Sensing Center, NORIS, or do you see that as, converging with them on what they do?
Great question. That is on the radar. Ed and I were just chatted about that yesterday. So this isn't just me. It's a community snow modeling effort, and we want to bring other community. We want other ideas. AJ and I were talking earlier, like, what are your ideas? How should we evaluate a model? And it sounds like I'm kind of becoming the lead for that. So I look to your support to help develop that team. 1, 2. Oh, Fred.
Can you comment on how well a 1 kilometer grid describes the topography of complex terrain?
Really, really good. No. That's a great question right there. I mean, obviously it doesn't. We have a prediction that's close to my house in Little Cottonwood Canyon. And man, it does the snow-tail site really, really good. But that 1 kilometer grid goes on a south aspect. It goes up to 11,000 feet, the valley at 7,000 feet, and then the north facing aspect at 7,000 feet. So we're going to be revisiting that. I don't want to do a grid. I'm not sure how to avoid that problem right now, but it'd be at least a much smaller spatial resolution so that we can kind of get the regionally topographically dominant characteristics in a watershed. Yes.
Yeah, I guess considering that, have you considered probabilistic maps of sweep?
Yes. I don't know. We're not touching that for yet. It is definitely that's next generations of the model development. We want to get something that we can make a deterministic estimate first, and then explore probabilistic methods later. Is that due to uncertainty in the model? Is that due to external inputs and probabilities going into it? An ensemble of models. I'm not exactly sure how that's going to look yet, but that's something we're definitely considering. All right, hopefully I didn't put you guys to sleep. Michael?
Our penultimate speaker will be Michael Kane, presenting on research to operations coordination. Short and sweet title for a short and sweet talk.
And you'll notice with the next talk, I have a very similar title too. So Matt Womble and I are both talking about just staff on board that are filling in some gaps embedded in OWP offices. I'm Michael Kane. I'm the director of the Center for Water Resources at RTI International. We have about 50 scientists and engineers working in the center, including 4 staff that are embedded in 3 different OWP offices in Chanhassen and Tuscaloosa and Silver Spring. The goals and objectives of this research is in OWP Chanhassen. They're doing work to support the Airborne Gamma Snow and Soil Moisture Program. You can see their results on no risk. In Tuscaloosa, this is Katie Van Werkhoven, sorry. She's looking at practical strategies of evaluating national water model forecasts. And then in Silver Spring, we have Zia Zhang supporting the development of the forcing engine for NextGen. So some key results here. I mentioned that in Chanhassen, they're supporting no risk, which just came up in the previous talk. And you see some of the, you can see some of the work results if you go to the No Risk website, actually. We do have a paper accepted this year at BAMS about using the snow the snow observations to improve forecasts. In this case, Carrie Olheiser, she actually flies in the plane flying over the snow courses in the winter to collect the data that goes into the SNODAS analysis. She coordinates with the river forecast centers to look at new flight lines in the off season and where they might need more information in order to improve their estimates of the snowpack. Really cool stuff there. In Tuscaloosa, this is Katie Van Werkhoven's work, and she gets thrown into action almost immediately after a flood event to do post-analysis, and she's looking at how good were the national water models. She spends lots of time developing visualization dashboards, and these are built on top of the verification system. Understanding there's a subtle difference between a full verification system and single event. Mine, but a lot of the back-end tools are very similar. And we also have staff in Silver Spring. This is Zia Zhang, who's working on the forcing data engine for NextGen. And as you look at it, meteorological variables, tons of different time steps, spatial resolutions, multiple models, both in forecast and framework. Who knows what data transfers to test. What are you gonna do? As far as impact assessment, its activities are constantly ongoing. One thing about having embedded staff is that they're constantly getting feedback from OWP on their activities. So it just is a great feedback of events that go there. And also every year we hear about, from Carrie's and Anders' work up in Chanhassen, the impact of their new snow information they provide to the river forecast centers to improve their modeling of the snowpack and resulting runoff. Next steps, like everybody else in this room, looking forward to the NextGen prototype, because that we mentioned earlier, that's what RTX is just getting started on. We see this as a potential landing place for almost all the research that we're doing. You know, we want to have that framework so we can really get things moving. I mentioned at the start that these are embedded staff. So that means I'm not doing the actual work. If you have really detailed questions, I will connect you with somebody. But I will take simple questions. Or you can just save them for Matt. All right, we'll move.
Okay, last but certainly not least, given that he is my boss, we have Matt Womble presenting on research to operations coordination between CIROH and the Office of Water Prediction / the National Water Center.
All right. Well, I'm standing between everybody and I guess the doors, so I won't take too much time. I will also caveat this presentation with the fact that still on paper, I'm still currently not the PI. That's still our old interim executive director, and I've been on the job for about 5 weeks, so I'm still learning what this is doing. And I'm also going to have a forward-looking perspective with this project. So we'll talk about sort of what the current state is, but then really what the forward-looking, because I think, and I'll encourage you all to think about this from your own projects, because the people that are here that are working on these sort of projects are going to be the conduits. I've heard many of you all ask throughout the course of this meeting, how is that R2O transition going to happen? And a lot of that is going to happen via the people that are being supported via the projects that Michael just talked about, but also the people that are being supported via this project. So Envision goal, it's a partnership that obviously CIROH optimize advancements in water science and operational capabilities will better serve public and protect private property. The Envision goal of the project is that the individuals supported via this, so people embedded within OWP, within the National Water Center, will support the efficient linkage and transition of research and science efforts underway at CIROH with those undertaken at OWP locations across the country. So again, this is the linkage that's happening between the CIROH projects, people embedded within OWP, some translators, the hopeful, to be able to help with things like transition planning, et cetera. The current state of play is that CIROH R2O staff, the individuals that are supported via this project, are really participating in research and development activities in collaboration with scientists and operational practitioners at the NOAA National Water Center and within OWP. So really they're supporting research activities relevant to CIROH, but really in direct support of OWP and the National Water Center. there's a poster out with all the individuals. You can see the 8 folks here. Many of you may be familiar with some of these folks. If you haven't, I encourage you all we'll try to create opportunities to meet them. They're all supporting and doing really great work. The National Water Center, some of the key results, some of the things that they've helped deliver. AWIPS 2 development. A lot of them have been working with RFCs on use of tools, education and outreach. There are specific social science and education components of some of the staff to be able to help implement channeling routing models, the National Water Model development of NextGen. Help with, obviously, we heard about it yesterday from Fred with total water level. These folks have been helping with that. Hydrofabric development efforts. Just a summary of many of the things that these folks have been working on. And again, as these folks work on these projects, and eventually as we think about the transition of CIROH projects, we'll be trying to find linkages between the skill sets of these individuals and then the scope of the projects that are being undertaken, and who can naturally align with what projects and help to see the transition of projects once they become mature enough into OWP. So that's the eventual transition, which is a good segue into the last slide here, impact self-assessment, the outcomes that these folks are working on, what they have been largely aligned with the expected outcomes, and the employees are making really valuable research contributions to OWP. And that's a great step for where we are currently, where we are within CIROH, from the maturity of the projects that have been funded. But the eventual, again, what I've been alluding to is that the eventual transition of these employees more from taking direct research and development activities within OWP to becoming more integrated within CIROH and helping to be our research transition translators from those CIROH projects into OWP. And so that's the work that we have over the course of the next year to be able to try to position these people, probably grow the pool of people to be able to better support that and better integrate them within the projects that you all are taking. So that is it. Hopefully that was short and sweet, and I'm happy to take any questions about any of that. Ed's giving me a somber look, so I must have said something completely wrong, or he's just.
Hey, Matt. Okay.
Oh, yeah.
I'm asking a question for Paul McGee from NOAA. He says, have the CIROH R2O staff visited any RFCs yet? And then he said also comments, if not, he says he's happy to help with someone to explore this opportunity.
So I believe that some of the R2O staff have. I know Juicer specifically has been working with some of the RFCs. I'm not sure if he's physically visited the RFCs, but I'm looking to Ed, and Ed's nodding his head up and down. So, but yes, we need to. One of the goals, one of the things that we need to do for this next year is better integrate the R2O staff directly with the CIROH network. We're going to need to have them here at these meetings, obviously, to meet with folks. So that will be a change, but also make sure we're working internally within. With OWP folks to make sure that they're engaging with the broader network of weather service folks that they need to, including RFCs. So.
Hey, Matt,
Fred?
Quick question. A year ago, Senator Shelby came and talked to us, and I was really looking forward to that. I was looking forward to getting kind of a perspective on what was his thinking in making this a reality. And I was wondering, he basically told us water's important, and he's glad that we're working on it. But he didn't give us a lot of kind of insight to what he was thinking in creating this. Can you maybe expand on his answer a little bit?
Well, I won't. You never speak for a boss or a former boss, so I won't speak for him or pretend to. But yes, as I think many of you know, there was the vision of what has been established here at the University of Alabama around water was the result of a lot of people have worked, but really was an initial vision that Senator Shelby and a few others at the university had around water. And I think it's pretty simply put that water is both the most familiar substance in all of our lives, and it is the most important substance. So it's equally the most familiar and the most important substance for all of us. There's a number of different ways in which you can take a research agenda with water. It can go in a number of different ways. I think obviously the co-location of the National Water Center being on campus here put the emphasis and focus on really flood and natural hazard component of that water related research. And I think as that began and continued to blossom and the successes of the National Water Model, the successes of things like the National Water Model, you saw the clues of what could be built eventually came together in his mind and the minds of others, that you could build, you could solve a lot of problems across the United States with providing resources to better support forecasting around water hazards. And I think he wanted to try to see that through, position the nation to be better prepared for water challenges in the coming years. And again, not speaking for him. I think there was one other question back, or maybe there wasn't.
I think that's a good question to end this session on. So
Okay.
thanks again, Matt.
And I just want to say again, thank you all for coming to Tuscaloosa. Thank you all for the participation in CIROH, the participation in this meeting. 5 weeks in, it's been refreshing and very heartening to see this assembly, see this amassment of talent, see the energy and excitement that is around CIROH. We obviously have a lot of work to do across the board, including us at Alabama, but excited to continue to get this going. And thanks again for coming here. Great to meet y'all.